All right, so what these wave functions give rise to are something called not orbits, but atomic orbitals. So again, an orbital is a general region in an atom that a certain electron is most probable to reside. So it's a region in space that holds electrons. Um, so again, orbital is very different from orbit. So they're not ringing around. They are actually, we don't know exactly where the electron are, but they're in a region in space that can be defined to a certain percentage. Um, so anyway, this quantum mechanical model specifies the probability of finding an electron in a certain region in space around the nucleus. And there are 4 quantum numbers that help us characterize what an orbital is and where electrons are found. Okay, so there's these 4 quantum numbers. Each electron is defined by 4 quantum numbers. So I'm going to go through the different quantum numbers. Okay, so let's define them. So the first quantum number is called the principal quantum number. It's given the symbol n, and this is the same n that we've already been talking about. It tells us which energy level the electron sits on. There's the angular momentum quantum number, which is given the symbol kind of a cursive L. The magnetic quantum number is m sub L, and then the spin quantum number, which is m sub S. So we're going to define each of those in turn. The first 3 define the wave function for a particular electron. In other words, tells you the probability of where the electron is. And then the 4th quantum number actually refers to something called the magnetic property or the spin of electron. Okay, so the principal quantum number n, like I said, is the one that we've already been talking about. It represents the shell number, or the energy level, in other words, the energy level in which the electron resides. So not all electrons can be in the same place, and because they all kind of repel each other. And we talked about how we have our energy levels. And so we said that similar to the Bohr model, we have the first level is n equals 1, and the second level is n equals 2. I'm not very good at drawing, but n equals 3, n equals 4, and so on. So it's the energy level that the electron in question resides in. So once we know what n is, we'll know where the electron is located. So n can be any positive integer greater than 1. So it can be equal to 1, like I said. It can't be 0. There's no 0 level, but there's the first level, the second, third, fourth, fifth, sixth, seventh. So up to infinity, where the electron no longer exists with that atom, but any integer greater than 1. Of course, the smaller n is, the smaller the orbital, the lower in energy it is. And the smaller n is, the lower the energy. Just said that. So if n equals 2, the energy is in the second shell, which is higher energy. N equals 3 is the third energy. Every once in a while, I won't use this, but every once in a while it shows up. Sometimes capital letters are used to indicate which shell we're talking about. So n equals 1 is sometimes called the K shell. And for n equals 2, it's sometimes called the L shell. And n equals 3 is the M shell. And n equals 4 is the N shell. And I don't know why they need to even complicate things more. I'll just refer to them as the first, second, third, fourth. But this may come up at some point, so I just wanted to warn you about it. If you see that, you know what it means. All right, so again, even though, they're not orbitals with electrons circling, however, the region in space kind of is the first level, the second level, the third level, and we increase energy. So sometimes when I drew it before where it's just like this, just think of the nucleus down here. It's just like a little, I'm just drawing sort of a little portion of this where the energy is coming out from the nucleus. Okay, so the second quantum number, which is the angular momentum quantum number, will tell you which subshell you are within a given shell. So you could kind of think of it, it's not exactly true, but you know, if we have our different levels, 1, 2, 3, and then within each level, there's sort of like sub-levels, you know, so there might be, drawing, not a very good drawer, but there might be it turns out that on the first level, there's just one. On the second level, there's actually 2 sub-levels. On the third level, there's 3 sub-levels, and so forth. We'll talk about that in just a second. Each subshell has a different shape, and we'll talk about that at the end also. So again, every main shell is subdivided into subshells, and within each shell of quantum number n, there are always n subshells. So like I said, if I'm on n equals 1, there's just one subshell. If I'm on n equals 2, there's actually 2 subshells. If I'm on n equals 3, there's 3 subshells. And if I'm on n equals 4, there's 4. And if I go up to n equals 5, there'll be 5. Like I said, they each have a distinctive shape, which we'll look at after a little while. But here's how the rules about this quantum number. What can L equal? L can have any integer value from 0 up to n minus 1. So again, it will depend on what n is. So if n equals 1, let's just kind of go through it. If n equals 1, L can only equal 0 because it can go up to n minus 1. And if n is 1, it can go from 0 to 0, so it can only be 0. But if n equals 2, L can equal 0, because it can always equal 0, but it can also equal 1, because if I plug 2 in, 2 minus 1 is 1, so it can also equal 1. Now it can't equal 2, because it has to be only up to 2 minus 1. All right, so then if n equals 3, that means L can equal 0. It can equal 1, because 3 minus 1 is 2, and it could be anything between 0 and 2. So it can be 0, 1, and 2, but they can only be integers. N equals 4, then L can equal 0, 1, 2, and 3. So now you can see why there are n subshells. So on the first shell, there's only one subshell where L equals 0. On the second shell, there's 2 possibilities for L, 0 and 1. So that tells me that there's 2 subshells. On n equals 3, there's 3 possibilities for L, so that means there's 3 subshells. And so there's always one 0. I don't know who made up these rules. I'm just telling you what the rules are. And I might have made it. I'm sure there was some meaning behind all these things. So there's the same number of subshells as whatever that shell number is. It doesn't get the shell number, but it does have the 0. So 0, 1, 2, 3, there's 4 of them. Different subshells are denoted by letters. So it turns out that if L equals 0, I'm talking about an S. It's given a name. So if the value of L is 0, then I'm calling that an S subshell. If L equals 1, that's called a P subshell. If L equals 2, that's called a D subshell. If L equals 3, that's an F subshell, and so forth. After G, we just kind of I think we skip I, H, J, K. We're not going to worry about it. We're really not going to go beyond maybe H. Okay, so what does that mean over here for what I was doing? Well, if L equals 0, that's an S. So on the first level, I have a 1S subshell. On the second level, L can be 0, so I can have a 2S subshell. That's its name, 2S. And then I also can have a 2P subshell. It's kind of hard to see, but 2S and 2P. On the third shell, I can have a 3S, a 3P, and a 3D. On the fourth level, I can have a 4S, 4P, 4D, and then 4F. So we just keep adding. Every new level adds one more subshell. So we talk about the subshells as whatever shell they're on, so 1, and then what kind it is, S, 1s. Now, if n equals 1 and L equals 0, that tells me my electron is in the 1s subshell. If n equals 2 and L equals 0, that means I'm in the 2s subshell. If n equals 2 and L equals 1, that means I'm in the 2p subshell. Hopefully, as you just keep kind of going with the flow and seeing if what I'm telling you makes sense, and I'm going to kind of review it all at the end, and hopefully it'll come together for you. Okay, so the third quantum number is called the magnetic quantum number. It's given the symbol m sub L, and it distinguishes something called orbitals within a subshell. The different subshells can have different shapes. The different orbitals actually have different shapes, but they also have different orientations in space. And hopefully that'll make sense in a few minutes. So each subshell, like I said, is subdivided into orbitals. And each orbital, so any orbital of any kind, can hold 2 electrons. So any orbital can hold 2 electrons. The rule for m sub L is that m sub L can be equal to any integer value from negative L to positive L. So let's kind of work through that. So if L equals 0, I'm going to erase this, so put that over there a little bit. So if L equals 0, remember what I just said on the previous slide, that means I'm in an S subshell. So I'm in an S subshell. And what's the rule? If L equals 0, m sub L could be anything from negative 0 to positive 0. So any integer between negative 0 and positive 0, which of course is only 0. So m sub L will only equal 0 if I'm in an S subshell. If I'm in a P subshell, which is L equal to 1. So if L equals 1, I'm in a P subshell. And of course, if L equals 1, m sub L could be anything from negative 1, any integer between negative 1 and positive 1. So that means m sub L could be equal to negative 1. It could be equal to 0, because that's an integer in between. And it could be equal to positive 1. If I'm in a D subshell, that means L equals 2. If L equals 2, then m sub L can equal everything from negative 2, any integer, from negative 2 up to positive 2. And then let's do the F's as well. If I'm in an F subshell, that means L equals 3. And so what can m sub L equal? It can equal negative 3, negative 2, negative 1, 0, 1, and 2, and 3. So this is what I mean by this, which means there are always 2L plus 1 orbitals in each subshell. What does that mean? Okay, if L equals 0, there's 1 orbital. If L equals 2, I'm in a P subshell, L equals 2, that would be, oops, sorry, back up. If L equals 1, I'm in a P subshell, 2 times 1 plus 1 is 3. So there's 3 orbitals, and these are the 3 orbitals, negative 1, 0, and 1. If L equals 2, then there are 5 orbitals, and these are the 5 orbitals. And if L equals 3, there are 7 orbitals. 1, 2, 3, 4, 5, 6, 7. So there's always, so the numbers are 1, 3, 5, 7, 9, 11, 13. They'll just keep going up the odd number. So there's always 2L plus 1 orbitals in any subshell. If I kind of, I think maybe I'll do it on the next slide. Oh, each orbital within a given subshell has the same energy. I'll show you that on the next slide. So I'm not going to talk about the spin quantum number, but let me draw you something here, and then I'll erase it before I talk the spin quantum number. So remember that we have our energy levels. N equals 1, N equals 2, N equals 2 up to 4. And then we said within each level, so that's n 1, 2, 3, 4, any integer. And we could go 5, 6, 7, on and on. We said that within each shell, there are n number of subshells. So that means on the first shell, there's only one subshell. But on the second shell, we're going to have 2 subshells. And we start to talk fast, and we're having subshells all over the place. Okay, on the third shell, we can have 3 subshells. And I've run out of room, but on the fourth shell, you get the idea, we can have 4 subshells. So we just got through going through the quantum numbers. So for n equals 1, the subshell then L equals 0, which means this is a S subshell. So I call this the 1s subshell. On the second shell, L can be equal to 0 or it can be equal to 1, which means I have a S subshell and a P subshell. So there's a 2s and a 2p. There's only a 1s. On the third level, L can be equal to 0, 1, or 2, which means I can have an S subshell or a P subshell or a D subshell. And then on the fourth, again, if we follow this, if L equals 0, 1, 2, or 3, that means I can have an S, P, D, F. And I know I'm getting kind of crowded in there, but hopefully you get the idea. Now, these are subshells. So there's 2 subshells on the second shell, 3 subshells on the third shell, 4 subshells on the fourth shell. And they are 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 1s, so forth. Now, the third thing we talked about was the m sub L, and the m sub L is the orbitals. And they're all at the same energy level. So one thing we'll talk about in a second is that the subshells can be at different energy levels. So the P subshell is a little bit higher energy than the S, and the D is a little bit higher than the P, and so forth. But the orbitals are on the same, for every energy level, we have orbitals. And remember I said that anytime we had an S subshell, since L equals 1, then M sub L could only equal 1, or could only equal 0, which means there's only one orbital. So I'm going to draw orbitals like this on that subshell. So there's one orbital. I'm going to represent that with a little box. The same thing's going to be true here because, let me try to use another color. So it's a little easier to see. So they're on the S level, no matter what, and again, I've got them kind of crowded, but on the S subshell, no matter what level I'm in, because L equals 0 for any time I have an S subshell, M sub L can only equal 0, which tells me I only have one orbital on any S subshell. But if for a P subshell, remember that L can equal 1. L equals 1 for a P subshell. And we just got through going over this. That means that M sub L equals 0, -1, or 1, which means that there's 3 orbitals. So on any P subshell, no matter where it's located, there are 3 P subshells, which means there's 3 regions that can hold, remember what's an orbital, it can hold 2 electrons. So on the 3p, there's 3 of them. On the 4p, there's 3 of them. On the 5p, there's 3 of them. No matter where the p is located, there's 3 orbitals. And then let's go ahead and do the d. So for d, L equals 2. Remember, that means M sub L could be -2, -1, 0, 1, and 2, which implies that there's 5 orbitals. So now here, there's no D subshell on the second. There's no P's on the first. There's no D's on the second, but the first time we get the D's is on the third, and there can be 5 orbitals. So on this D, there's going to be 5. Run out of space. Let's go back to my green and maybe draw my last line up here. So there we go. All right, so SPDF. One more. let's just go ahead and finish this off. So F means that L equals 3. So that, remember, that means there's 7 possibilities. -3, -2, -1, 0, 1, and 2, and 3. 7 possibilities, which means every time I have an F subshell, there's 7 orbitals. So it just keeps drawing. So let's go back to the green. This one's green. That one's green. I guess it doesn't really matter. But this is how it's going. So N tells us what shell we're in. L tells us which subshell we're in, S, P, D, F. M sub L tells us, first of all, how many orbitals, and then, in fact, it can tell us which orbital we're in. And then finally, our last quantum number is called the spin quantum number, and it refers to the 2 possible spin orientations of the electron. So if you put 2 electrons in close proximity to each other, they're going to repel each other. But they have this way, so we know that an orbital can hold 2 electrons, and these electrons have a way of kind of hiding from each other, and they do something which is spin. So if here's an electron, this one may spin in this direction, and the other electron may spin in the other direction. And so they create magnetic fields that kind of hide from each other. But anyway, the idea is that they have 2 spins. And so M sub S can have 2 values only. And I don't know why they came up with 1/2. There must be some reason behind it. But M sub S could either equal 1/2 or -1/2. How do we represent that? Let's try purple, see if that'll show up. If the spin is +1/2, I represent that with an arrow going up. If it has a -1/2, I'll represent that with an arrow going down. I can only allow 2 electrons in any orbital, but every 2 electrons will have opposite spins. And we'll talk about this in just a minute. So this kind of helps us see the whole thing. So N can equal 1, 2, 3, 4, 5, etc. If N equals 1, L can only equal 0. M sub L can only equal 0. That means I'm in a 1s subshell, and that there is only 1 orbital in any s subshell. If I'm on the second level, N equals 2. Maybe I need the yellow. Okay, N equals 2. I can either be 0 or 1. L can be anything up to 1, 0 or 1. If L equals 0, M sub L only equals 0. That tells me I'm in an S subshell, so that's 2S, and there's only 1 subshell. But if I'm in the 2, if N equals 2 and L equals 1, that tells me I'm in the 2p subshell. There's 3 possibilities for M sub L, which means there are 3 orbitals in on the second shell, on the 2p shell. So total on the second shell, I actually have 4 orbitals, 2s and 2p, 1 2s and 3 2p's. Okay, now when I go on the third shell, L can be 0, 1, or 2. If it's 0, then I'm in a 3s, and there's only 1 orbital, 1 possibility. If I'm in, if L equals 1, then I'm in a 3p subshell. There's 3 orbitals with the values -1, 0, and 1. If I'm in if L equals 2, that means I'm in a 3d orbital, and these are my 5 values, meaning I have 5 orbitals. The 5 values of M sub L if L equals 2. And then finally, let's go ahead and do purple again. So if I'm in the 4th shell, now I have 4 options for L. I could either have a 4s, 4p, 4d, or 4f, depending on 0, 1, 2, 3. Again, if L equals 0, so anytime I'm in an s subshell, I can only ever have 1 orbital because the only value of M sub L can be 0. But if I'm in a p subshell, there's 3 values, 3 orbitals. If I'm in a d subshell, there's 5. 4d, there's 5 orbitals. And now when I'm in the f subshell, there's actually 7 values of M sub L, which means there are 7 orbitals on the on the 4F subshell. Okay, so hopefully that makes more sense. This is kind of another way of looking at it. So here we have the first shell, here we have the second shell. This actually doesn't show. I'll show you another one in just a little while. Actually, like I said, the 2P is actually slightly higher than the 2S. The 3P is slightly higher than the 3S, and the 3D is slightly higher than the 3P. So they're not really all on the same energy level. They're all similar, but anyway, you can see here that the S's always have 1 orbital. Starting on the second level, we have the P's, and P's always come in 3s. Starting on the third level, we have the D's. The D's always come in 5. Starting on the fourth level, we have the F's. And then the F's will continue, and then we'll have the G's, and then we'll have the H's, and so forth and so on.